Hi guys, Buildzoid here, and today we're going to be taking a look at another DDR5 overclock with Ryzen. This time, the setup here is a Ryzen 9 7950X on an Asrock B650 live mixer with a G-Skill Trident Z5 RGB. You can read the rest of that part number yourself. Memory kit. The memory kit was provided by G-Skill, so big thank you to them for sending that over. And the motherboard and the CPU were purchased by me, so big thank you to the supporters of the channel for making those purchases possible. Anyway, the G-Skill memory kit that I'm using here is based on Hynix 16 gigabit A die. It's a 7800 CL36 XMP memory kit. And the reason I'm using this memory kit on the B650 Live Mixer is to test the new AGESA 1007B. Because Asrock has released a BIOS for the live mixer with this AGESA. They were actually one of the first motherboard manufacturers to release BIOSes with this new AGESA. And the thing with this new AGESA is that AMD's basically significantly retuned the memory controller and improved the memory training routines during startup. So it makes it possible to run significantly higher memory clocks, which is why I'm using a 16 gigabit, Hynix A die kit that's spec'd for DDR5-7800. Now, the kit is actually underclocked here a bit because, well, at 7800, achieving stability is just not very easy to do. So we're at 7600, and I'm just going to move testmem5 out of the way. So yeah, we're at 7600 megabits per second, so 3.8 gigahertz on the memory clock. The memory controller is at 1900 megahertz, and the Infinity Fabric is at 2067 megahertz. So this is all desynchronized. The thing is, you technically can. So yeah, in 2-to-1 mode, you can actually synchronize the Infinity Fabric to the memory controller clock, but the Infinity Fabric only has ratios for like 1800 and 2000. So you can't synchronize to 1900, which is really silly. And unfortunately, at 1800, your memory clock is so low that the performance sucks. And at 2000, your memory clock is so high that the stability is basically impossible to get working. So yeah, so this is 20. So here we are at 2067 and 1900 on the memory controller and 3800 on the memory. You can see the timings down here, though that's not really that important right now. Here's the stress tests that I've ran. So testmem5 on the Extreme 1 Anta 77 preset that ran for 4 cycles and just under 2 hours. Then we have a HCI mem test overnight, which ran to over 1000%, no errors. I've not run YCrunch or VST. I don't really think there's much point in running that because, as we'll see, like I've done a lot of like performance testing on this. So as we'll see, I don't really care that much about stability with 2-to-1 mode at like 7600 because you wouldn't really want to run this anyway. But this is more to show that like, hey, you can actually get 7600 stable. So yeah, here's a 155 loop run of Linpack Extreme, and that's on the 10 gig dataset size. Linpack Extreme actually works really well as a stress test on Ryzen 7000. In fact, in some scenarios, it's heavier than YCruncher. So, yeah, but obviously I would also, like, if I was actually serious about dailying this, I would also include a YCruncher run. There's just not much point in doing that, in my opinion, because, well, let's take a look at some performance numbers, shall we? So 6200, like DDR5 6200 with 30, 3630, like these timings over here, which is a very basic memory overclock for Ryzen 7000. Pretty much any CPU should be able to do this. Admittedly, there are some absolute potatoes that on older AGESAs would get stuck at like 6000. But with the new AGESA, even in 1-to-1 mode, you can actually hit higher clocks. So a bunch of my CPUs, like the 7950X that I'm using here right now, previously wouldn't work at 6400 basically at all. Whereas with the new AGESA, it is actually possible to get into Windows at 6400 and even run some benchmarks. It's just not very stable, so not really, like I don't have like comparison data for 6400 because running Linpack at 6400 is not really an option. Something like PyPrime or IDA, that'll run, but yeah, Linpack won't. But anyway, so 6200 CL30 is very, very doable with pretty much any Ryzen 7000 CPU, especially with the new AGESA. And so that's sort of my like one-to-one mode comparison, because that's like a basic one-to-one mode overclock in my opinion. Or more like basic, it's not necessarily an overclock if you have a memory kit that's spec'd above 6200, but you get the idea. And then we have 7600. I actually did manage to run some benchmarks at 8000, like DDR5 8000. Unfortunately, the stability is so bad and also really inconsistent. Like reboot to reboot, it would kind of come and go, that I couldn't run like a full set of benchmarks at 8000 yet. Maybe if I go through all of my motherboards, I might, and also all of my CPUs, I might find one that'll actually like run 8000 long enough to run everything. Unfortunately, the thing about the 2-to-1 mode is, like, from a memory latency perspective, it's not great, right? PyPrime, it's not that bad, though. Like, that's still worth noting. Like, PyPrime isn't massively slower in 2-to-1 compared to 1-to-1, and that's even at just 7600. Well, IDA latency is really bad, though. I don't really put a lot of stake in IDA's latency test. I don't have IDA bandwidth numbers because they don't really make any sense. Like, IDA's like even on Intel CPU, IDA spits out like physically impossible memory bandwidth numbers on a regular basis, but with Ryzen, it's like a whole nother level of like these numbers don't make any sense. So we're not going to have any IDA bandwidth tests. I've also ran time by CPU test, which generally would be kind of like a memory bandwidth bound test. Yeah, that actually performed better on one-to-one mode, 6200 CL30. 3D Mark 11, which is another, well, actually, that scored the same for both configurations, which was kind of surprising because I generally consider that a relatively memory latency intensive test. But yeah, and that's like the 3D Mark 11 physics test, not the entire benchmark, but specifically the physics benchmark. Yeah, so that actually spat out the exact same score for both 7600 and 6200 CL. For 7600 and 6200. Y-Cruncher actually sped up. Linpack slowed down, to my great surprise. Like Y-Cruncher, everybody, like we all know Y-Cruncher is a massive memory bandwidth hog, so it makes sense that it actually benefited from 2-to-1 mode. But Linpack slowing down is really surprising because Linpack is normally about as bandwidth heavy as Y-Cruncher is. At least in the DDR4 days, Linpack was just completely a memory bandwidth test, and it didn't really, like, admittedly, it would pick up certain timing issues that, like, IDA wouldn't pick up, but in the grand scheme of benchmarks, if you had the choice between sacrificing some latency for more bandwidth, you would always go for more bandwidth for Linpack. Whereas there are other benchmarks where you'd go the other way. But yeah, with DDR5, you actually have so much memory bandwidth available just basically always that Linpack turns into a bit of a latency benchmark instead of a bandwidth benchmark. And so yeah, 2-to-1 mode actually is very slightly slower than 1-to-1 mode. For Linpack 10 gigs, which, yeah, that is interesting. Then we have some synthetic memory bandwidth tests. This is from the Micro Benchmarks GUI, so that's this software over here. This produces far less ridiculous bandwidth numbers than IDA does. In general, this is just a better benchmark than IDA is. So I prefer using this. And honestly would recommend that you use this too. It's a bit hard. It's not super like beginner friendly because it spits out a lot more data than IDA does, but it's better than IDA. So anyway, also it's free. We're like, yeah, anyway. So micro benchmark, read bandwidth, 32 threads, AVX 256, 2-to-1 mode wins. Yay, it has more bandwidth. I mean, we already know that because Y-Cruncher likes it. And then there's also the add test, which is another like slightly more complex bandwidth test. And there's more bandwidth in 2-to-1 mode, but the latency is slightly worse, right? So there's also a latency test, and that worked out slightly worse for the 2-to-1 mode. So basically 2-to-1 mode, if you're at like 7600, is kind of a wash in terms of performance. Like, yeah, you get very slightly more memory bandwidth. Your latency is very slightly worse. And overall, it doesn't really make a difference, but maintaining stability is a lot more difficult than at 6200, because at 7600, your signal integrity becomes far more of a problem than it is at 6200, right? Like as you crank the clock speeds up, stability just generally becomes a bigger and bigger problem. But the performance really didn't change very much, right? Like the biggest like right now, my view, like my thoughts on 2-to-1 mode is basically like, well, if DDR5 8000 worked, you can actually get like at DDR5 8000, you can actually get Pi Prime to like perform well, and Pi Prime is a really memory latency, like really latency sensitive benchmark. Um, and I do have some runs, like I did manage to get some runs of Pi Prime in at DDR5 8000, and they looked good. The only issue is it's really unstable. So, it's like, so 2-to-1 mode, basically, if you can get DDR5 8000 to work, it might actually be viable, because the latency actually starts being competitive with 1-to-1 mode, and you do get slightly more bandwidth. But at the same time, it's worth considering that, like, unless you have a dual CCD CPU like a 7950X, I don't really think there's enough cores in your typical CCD to actually need the level of memory bandwidth that you can get out of 2-to-1 mode. Um, maybe DDR5 8000 in 2-to-1 mode is also able to actually just beat Pi Prime beat like the memory latency of 1-to-1 mode on just like sheer brute force, of the memory going so fast. Like, because there's a lot of timings that don't actually change as you go from like 6200 to 7600. Um, and so there are some, like, performance benefits to the extra clock speed, even if your memory controller's getting underclocked. Um, but yeah, like the DDR5 8000 is like too unstable to really like have good performance data with it. So yeah, obviously, like, more testing to be done. This is like initial testing, right? Like, this is literally the first board. Yeah, this is one of the first boards that I have to get this update. Gigabyte only recently put out BIOSes with the AGESA 1007B, so I think they put out an update for the Tachyon. So I'll have to check that, because that's a 1 DIMM per channel 10 layer PCB motherboard. So maybe that'll actually make like DDR5 8000 viable with my CPUs, and then we'll see, maybe 2-to-1 mode actually not be a complete, gimmick that only really helps in Y Cruncher. But yeah, unless you're at basically, I would not really bother with 2-to-1 mode outside of like synthetic benchmarks. Right? Like, yeah, there's a competitive scene for Y Cruncher, so for Y Cruncher it makes sense. For everything else, like 1-to-1 mode is gonna work just fine. Um, Also, my 1-to-1 mode here, like, if I spent as much time on the 1-to-1 mode as I spent on 7600, because this is just something I just kind of threw together. If I spent as much time on 1-to-1 as 2-to-1, I think I could have, I could have pushed 1-to-1 mode even further. So the fact that like 2-to-1 mode is struggling to inch past 1-to-1 mode, where 1-to-1 mode, in my opinion, is kind of, low effort settings, it's not a great sign. So, yeah. Anyway, other fun things you can do with the new AGESA, is you can do DDR5 8000 on like everything. Like, here's an Asrock B650 HDV, right? Literally one of the cheapest B650 motherboards you can buy, and yeah, it boots 8000. It does not run 8000, as you can see in just like 4% of HCI mem test. It managed to produce 79 errors, so the stability is amazing. But like, it's like on par with Intel memory controllers now. Um, but actually, Intel at 8000 is actually easier to stabilize than this is. But, or well, I shouldn't say stabilize, because the issue I have with Intel is if you just run the stress test long enough, you'll inevitably get errors at some point. Um, with the AMD memory controller, you get errors pretty consistently within like the first hour, if it's not stable. So, but anyway, so yeah, this is like it's impressive that this boots at all, because I have Z7, like there are Z790 motherboards out there where you will just not be able to boot at DDR5 8000 whatsoever, right? Like, you won't even be able to take a silly screenshot like this because it just won't post. So the fact that this posts at all on such a, budget motherboard is kind of neat. but in terms of practical applications, they are non-existent. And also, the HDV, even at 7600, really wasn't being particularly well behaved, which is why I ultimately switched back to the live mixer to make this like 2-to-1 mode stable overclock. Anyway, here's the live mixer doing 8000. This is the most stable 8000 configuration that I got. I have no idea how there's like a block of 1024 errors. I really not sure what would cause that. It might be like an entire like set of writes went wrong or something, because I think that might be an entire column, I think is the right term, of errors, like where it just like an entire, yeah, like an entire set of addresses is just wrong. Um, so that's kind of fun because yeah, like those errors started showing up, and I was wondering like, hey, are they gonna spread out? But nope, just 1024 errors and then nothing after that. But not stable, and this is of course DDR5 8000. But you can see that we were almost getting to 100% coverage on HCI here. And in fact, I think I even got as far as getting testmem 5 to pass at 8000, but then HCI errored out in like 100%. So, yeah, at 8000, also 8000 is just really inconsistent. Like reboot to reboot, and as you make setting adjustments, the stability seems to like come and go kind of randomly. So might be the board, might be the memory controller, needs more testing. Yeah, I don't have like good data for 8000 because, well, it doesn't run well enough with the boards that I've been trying so far. But anyway, so that's sort of what the new AGESA enables, is basically 2-to-1 mode to not be completely useless, because previously 2-to-1 mode, like if your CPU did like 6400 in 1-to-1 mode, it probably also did 6400 in 2-to-1 mode. So the fact that you can like do DDR5 8000 at all is like kind of neat, but practical uses, like it's good at Y cruncher. It's like the one thing it's good at, is just like, yeah, it's really good at Y cruncher. Also synthetic bandwidth tests, which Y cruncher basically is a synthetic bandwidth test, but it's an actual calculation. It's not like IDA where it's like intentionally uh like trying to hit peak bandwidth. It's just a really memory bandwidth bound algorithm rather than like a synthetic bandwidth test. Um, Everything else is like you can get similar performance in 1-to-1 mode, if not better performance in 1-to-1 mode. So yeah, 2-to-1 mode, fun to mess with, not actually useful. But anyway, if for some reason you did want to spend a whole bunch of time trying to stabilize 2-to-1 mode, you can do things like 7600 CL34, which is what I have here. And yeah, like it passes LinPack, it passes HCI. I've not checked if this is retrain stable, which is a real concern. Also with the new AGESA AMD, thanks to like the better training routines, the memory context restore function should be a lot more reliable than it used to be. Because the, like, you know, you might remember in some of my past like Ryzen memory overclocking videos, I recommend to disable memory context restore. And the reasoning for that is partially it causes issues if you disable power down mode. But the other issue is that because the memory training wasn't particularly great, if you used memory context restore, your system would just sometimes not be able to post. Like it would try to use the old training parameters and it would just not work. So you'd just get you'd get stuck in boot up. Because the idea behind memory context restore is that if you have a robust memory training algorithm, you can use your old training data to reboot the system without having to go through a whole set of training again. But if your training data is garbage because your training algorithm wasn't particularly good, you take your garbage training data and you try to reinitialize the memory with it, and it just doesn't. Right? So, and I'll have a video covering memory training in more or like what memory training actually is in more detail in the future. A lot of people make the mistake of thinking that memory training configures like basic memory timings that you play with in the BIOS. It doesn't configure that. Memory training is about getting the memory control, like it is about configuring like far lower level operating parameters for the memory controller and memory. And so manually setting all of your memory timings will actually make no difference to how good or bad the memory context restore function does at actually like rebooting your system. So with AGESA 1007B, memory context restore should be a lot better. And I haven't run into any issues with it, which has been really nice when like tuning the, like so far I haven't run into any issues with it, but you know, like I also need to do like a full system power down reboot, see if it retrains properly, that kind of thing, which I'm not sure if I'm going to bother with that because like I mentioned, like from a performance perspective, 7600 CL34 is really like it looks neat. It's not actually particularly fast though, so yeah, I don't know. Like, but I haven't tested the retrain stability. I've been using memory context restore with it so far. That seems to be working just fine, which is really convenient because the new, more robust training algorithm is also way slower. Um, so yeah, like training, like basically making any adjustment to this that requires an actual retrain. So changing the memory VDDQ or the memory VDD voltage forces the memory to retrain. You can change a VDDIO without retraining, which is interesting. And also, if you change any memory timings, you need to retrain as well. So anytime I'd adjust a timing or something, it takes like forever to post because the training routine has to run and, you know, get the memory working again. But after that's run once, I've just been, you know, relying on memory context restore to handle boot ups, and I've not run into any issues with it yet. But that doesn't mean it's 100% reliable, right? But it should be better than it used to be. Um, Anyway, I guess let's take a look in the BIOS at the actual settings that I'm running here. Oh, and I also, this was all run with a fan sitting on the memory. And yeah, so let's take a look at the settings. Anyway, so we didn't just go through memory training because memory context restore is enabled, as you can see here. For the voltages, I have VDDIO at 1.42 volts, which is kind of high, but it should be safe. Then VDDs at 1.43, VDDQs at 1.35, VPPs at 1.8, which is just default VPP voltage for DDR5. The FCLK is at 2067 because 2067 works on every CPU in my experience. Like there are like most chips should do 2100, but sometimes 2100 doesn't work. And I really didn't feel like, you know, dealing with Infinity Fabric related instability with this cuz like the priority was getting the memory overclock. So 2067 on the Infinity Fabric. We're in 2-to-1 mode, of course, for 7600 to work. The SoC voltage can be actually quite well, it does. I don't have it all the way at 1.3 volts. I was messing with it at like 1.3 volts for like DDR5 8000, but I never really made much progress at DDR5 8000, and I got sick of the really long retrains. VDDPs at 1.15 volts. This is optimal VDDP for this actually for Asrock boards in general. I think their BIOS might actually be set up so like specifically for 1.15 volts VDDP because both the 17900X and the 7950X on both the HDV and the live mixer, like I set any other VDDP voltage and things just get worse. Like a lot worse. I raise it, it gets worse. I lower it, it gets worse. Like if you, yeah, like the stability literally can't even get into Windows if you mess with the VDDP. So 1.15, at least on ASRock boards, seems to be like the correct VDDP, and anything else doesn't work. Though it might also depend on how lucky you get with your, like maybe some CPUs will have different preferences. I would assume it's relatively motherboard specific as well, potentially. But yeah, on the ASRock boards that I've been using so far, and my 17900X and 7950X, VDDP at 1.15 is best VDDP. Literally anything else that I tried just like either didn't bring any improvement or actively made things worse. And I went like I tried more, I tried less. Um, yeah. 1.15 is, and also the board defaults to 1.15, so that's kind of neat. That like ASRock seems to have just figured out that yeah, we have designed for 1.1, like our BIOS is like tuned for 1.15, and 1.15 works best. At least from what I've tested so far. Anyway, I have spread spectrum disabled. This is just to make this BCLK float around less. Yeah, so let's talk about the memory voltages. So, VDDIO, VDD, and VDDQ. So, VDDIO is the voltage that the memory controller actually uses to talk to the memory. Right? VDD is the internal, like, core voltage of the memory chips. So this primarily affects your memory timings. VDDQ powers the I/O circuitry of your memory chips. So this is what your memory chips... Well, I'm actually not sure if VDD is used for setting the I/O voltage level, because I don't design memory chips, so I am not sure how exactly VDDQ and VDD are distributed throughout the memory chip. And I don't really like, well, yeah, so I'm not 100% certain on that. But VDDQ definitely powers the I/O circuitry, so at the very least, it affects the, like, rise and fall times for your signals, which means it sweet spots really hard. And it's just incredibly annoying to deal with. So, yeah, like, I ended up at 1.35 volts VDDQ because what I found is that at high VDDQ, the stability was getting actually worse. And also VDDQ is going to depend on your motherboard, like how, like what trace layout your board has, what terminations you're using. It's, yeah, like it'll probably vary by memory kit. Like this, and VDDIO is kind of the same thing. Where like if you set it too high, your stability gets worse. If you set it too low, your stability gets worse. Because this is another signaling voltage. So like both VDDIO and VDDQ directly affect the like signal integrity between the memory controller and the memory sticks, and so they sweet spot like really hard. And if you have them too high or too low, your stability is just bad. Or like you might not even be able to post. But yeah, so that's kind of the thing. And at 7600, what I found seems to work best. Well, I haven't checked if it's retrain stable. That's the other like issue, is that there is definitely at like DDR5-8000 and 7800, there seems to be some like retrain inconsistency where if you retrain, your stability might get better, it might get worse for no apparent reason. So if you're trying to like tune your voltages, it's an absolute nightmare because you'll like lower a voltage and your stability gets better, and then you'll change something else, like you'll change a timing, and suddenly your stability is terrible. And so you'll change that voltage again, and then your stability is still terrible. And then you'll undo the timing change, and you'll go back to the previous voltage level, and your stability is still terrible, right? So then you'll like reset the BIOS, punch in the most stable settings you've tested so far, and they're not stable anymore. So yeah, like, so I'm not even necessarily convinced right now that this right here is definitely like the ideal settings, because I've not done a whole bunch of like turn the system off, you know, like I'm not going to disable memory context restore. Like, I mean, like turn off the system, disconnect, like turn off the power supply, right? Cut 5-volt standby power, so that the board gets complete, like you get a complete cold boot from nothing. So that forces the motherboard to retrain. And then if it's still stable after like multiple forced retrains like that, then I would be confident in saying that these voltages here are actually optimal. But I figured I'd still make this video even without the retraining testing, because I find it really interesting that, like, at least with the Asrock boards, and I've noticed the same thing. Like, originally I noticed like the lower VDDQ seemingly being better on the HDV. So I think Asrock might just have the boards design, like either it's a BIOS tuning thing or it's even maybe just a trace layout thing where Asrock boards don't like super high VDDQ voltage. Or yeah, and like and also VDDQ sweet spots like super hard, like, and it can vary by BIOS version. So actually they probably changed something about their termination settings with these new BIOS releases, but yeah, just like basically, if you're tuning these three voltages, be open-minded because they like without like unless you have like a like a $500,000 oscilloscope so that you can actually look at what's happening to the signals. There's really no way to know what settings for these voltages are optimal because it varies by memory chip, by CPU, by motherboard, and by BIOS version. Um, and yeah, so these are the settings that I landed on that are like the first settings that it passes HCI, it passes TestMem5, it passes LinPack, but I don't know if it's retrain stable. So maybe I just got lucky on this, lucky as in like it trained just right this time, and if I reboot it a bunch of times, it might mistrain at some point, and then it won't be stable again. Or these are actually the optimal voltages. I just don't know because RAM is annoying like that. But I figured I'd show you these settings to just sort of like, if you're messing with 2-to-1 mode, consider using less VDDQ and more VDDIO. It looks super weird because you'd think like, wait, like maybe I guess maybe the IO circuitry on the CPU side of the equation is like slower than on the memory or something. So if you like drive the signal really hard on the memory end, you start having like reflection or ringing issues, which would be a side effect of like high VDDQ voltage potentially. I don't know. I don't have oscilloscope eyes. I don't actually know why at higher VDDQ voltages the stability seems to get worse, but like my best guess would be that probably ringing problems, where a signal like where the actual signals are just being driven too hard and they're distorting because of that. Arguably, if you set the termination just right, it might be possible to fix that, but it takes like forever to retrain. So I don't really feel like spending a bunch of time trying to manually tune the terminations, especially considering how many of them there are. But yeah, so this is really more of like hopefully these voltage settings inspire you to try things if you're in 2-to-1 mode that you wouldn't otherwise try, because I can't say that these are actually optimal. I haven't done enough testing on them, and doing enough testing on them is going to take forever. Yay. Anyway, let's take a look at the actual memory settings over here. I have gear down mode just turned on because this is hard enough with it turned on, or with it set to auto. DFE read training this gets enabled by default. When you, I think, yeah, Asrock enables that when you turn on the XMP, which you can see I have the XMP turned on. Interestingly enough, Asrock actually, when you load up a 1.45 volt XMP, they set the voltage to 1.4 volts. This is probably due to the fact that on certain BIOS versions for certain motherboards, there was a bug where if you wanted to go above 1.435 volts, it would glitch out. I'm happy to report that this BIOS on, actually, I'm not sure if the PMIC on these, wait, can we check the PMIC? Oh, no. Well, I'm not sure if the PMIC... No, these G-Skill sticks had issues with Gigabyte boards. So, yeah, I've not run in... Like, I've been able to raise the memory voltage to, like VDD voltage really high, and it doesn't cause issues. That used to be, like, on some BIOS versions, that's an issue where you can't go over 1.435 volts. It also depends on what memory sticks you're using. Because there's like certain power management ICs that just have like weird, like the way their high voltage mode is implemented is just weird, and so on some BIOS versions and some other boards it's broken. And DDR5 is just like truly designed for servers with no overclocking. Anyway, so yeah, this BIOS doesn't seem to have the like high memory voltage issues that some of the older BIOSes had. But at the same time, I didn't see any benefits from like really high memory voltages. And again, when you're at these very high speeds, there's a very real possibility that if you just shove more voltage into things, you don't end up with things, you get worse results, because instead of benefiting from faster switching speeds, which is the main reason why you would usually use more voltages, you can get transistors to switch faster, you potentially end up with like signal distortion issues that negatively impact overclocking. So there's, yeah, so that's why I'm like, Like, I experimented with, like, more voltage. I didn't really find any major benefits to it, though in theory, like, going high on the VDD might allow me to push some of the memory timings down, and hopefully won't affect the stability, but again, stress testing things takes forever. So, right, like, yeah, like, properly stress testing memory takes, like, a day at a minimum. And so, I'm not really in a rush to, like, go through every combination of settings to find out if, like, hey, it's safe to go 2-to-1 mode, high VDD voltage, and then just leaving the signaling voltages at whatever setting they're happy at, because, well, there are some, say, Intel motherboards where raising VDD forces you to raise the memory controller voltage. So, yeah, and Asrock seems to kind of be following that behavior, where it's like I/O voltage and VDD voltage kind of need to be similar, but I haven't done, like, a ton of in-depth testing on that. Also, because, like, initially I was trying to get DDR5 8000 stable, which really wasn't going anywhere, so I gave up on that and eventually tested the HDV, and then eventually decided, okay, let's just try, like, anything in 2-to-1 mode higher than 7200, because 7200 in 2-to-1 mode is actually useless. Okay? Like, if you're not going, like 7600, again, we're going to refer to the performance, right? 7600 is, like, kind of a wash relative to 1-to-1 mode 6200, but 7200 is actually just a straight downgrade, and there's nothing you can do about it. Like, 7200 is just bad. Do not run 7200. Either run, like, 7600 or 7800 or 8000, or run, like, 6200 or 6400. Or if you get really lucky, there are CPUs that can do 6600 in 1-to-1 mode. But yeah, there's, like, a nice big no-go zone between, like, 6600 and like 7600, where technically, yeah, in 2-to-1 mode you could run 6800, 7200, 7400. The performance is just absolutely useless. So I don't know why you'd want to do that. Anyway, back to back to the settings. So let's talk timings, because most of this has been spent on voltages, but let's talk timings. So 34, 44. This isn't, like, at 7600. It's reasonably tight, but obviously, if I ran more VDD voltage, maybe we could run, like, 7600 CL30 with, I don't know, like 1.6 VDD. I don't know if that would send the stability down the drain. It might. I did try TRCD 42. That did not work. 44 is, well, I didn't try 43, but, like, one tick of TRCD is just not going to make much of a difference. TRP's at 36. This isn't, it might go lower than that. TRAS is at 36. It might go lower than that. TRC's at 72. Might also go slightly lower than that. TWR is at 48, which, as far as I know, should be the register limit for AMD CPUs, but Asrock says it's 42. Requires more testing. 65,000 on the refresh intervals, that's completely maxed out. Then the refresh timings are all set to the same value. These two should still not be used, as far as I know. As in, like, you can punch in whatever number and it shouldn't affect performance, but I haven't re-verified that because, new AGESA, maybe AMD decided to use TRFC2 and TRFC's same bank. Is it same bank group? No, same bank. Yeah, because it refreshes the same bank in every single group, but you have the other banks still available. Anyway, so same, like, these two, previously these were definitely not used by AMD, so you could punch in whatever number and it didn't affect anything. They might be used now. I haven't checked again. They're probably still not used. I can't imagine that they've, like, completely changed their refresh procedure. Actually, well, they could have. But yeah, I haven't tested for that yet. So anyway, I've set everything to the same value because that's just, like, the lazy way of dealing with it. Also, when your refresh intervals at 65,000, the refresh cycle timings really don't matter that much in terms of, like, performance impact. TRTP's at 18, could probably go a bit lower than that. TRRDL at 8 and TRRDS at 4. TRRDL below 8 at, like, 7600 on 8i is not really a thing. in terms of stability. It tends to not work. Whereas TRDS at 4 is as low as it goes. TFAW at 20, which as far as I know should be the register limit for AMD CPUs, but again, Asrock seems to have extended that down to 12. I don't like the funny thing with a lot of timings is if you set them too low, the memory controller will just auto correct them for you to the like minimum value or some random value. I actually don't know exactly what, like, I guess it depends on how the memory controller is implemented. But yeah, so I have that at 20 because at least on gigabyte boards, that is still the like the timing limit, and I don't know that that's changed. Anyway, write to read, long and short. These are, I don't think these are minimized. Actually, no. Short, I think, is pretty close to as low as it goes, but long, I am not sure about. Then we have read to read, same chip select, which is at 9. Might go lower than that, but yeah, not, like, it won't go a lot lower. Like, at 7600, you're not going to run it at 4. Okay, like, that's like what you'd run it at, like, 6200. You're not doing that at 7600. Anyway, right to write, I have at 7. This might also go lower, but I've not checked. Then we have write to read, which is at 7, which might go lower. I'm actually kind of surprised that it's not at 6. And then read to write is at 22, which I think is actually pretty close to minimized for 7600. But yeah, so these are the timings that have worked for me. They're definitely not the lowest possible timings. They are reasonably fast. Like, they're better than an XMP profile, but, you know, that's not exactly difficult to do. Yeah, I don't know, maybe, well, here's the thing, is, like, obviously, you know, let's say that doing this doesn't completely break the stability. Then I would expect that, say, something like, actually, maybe TRAS would go down as well, so maybe we could, so maybe something like this could work. And then, I don't know, we could maybe, well, I'm not sure about TRFC. I'm just going to leave that at 511. The thing is, like, with refresh interval, like, with refresh timings, if your refresh cycle is 500 cycles and you're only refreshing every 65,000 cycles, you're spending, like, less than 1% of your runtime on refreshes. It really doesn't matter if you go from, like, 0.1, like, 1% to 0.9% refresh. Right? Which right now we're at, like, actually, I'm just going to pull up the calculator for this. So 511 over 65,535. Yeah, we have a 0.7% refresh cycle. Or like 0.77% refresh cycle. And it's like, yeah, maybe something like TRFC 400 at 65,000 would work. And we'd have a 0.6% refresh cycle, which is such a big difference. Right? Like, so, yeah, I would not actually bother with messing with the refresh cycle, because it like, once your refresh interval is this high, the refresh cycle stops really mattering that much. Like, you know, it's one thing if it was at, like, 1,000, then yeah, that would kind of be a big deal, but going from, like, 500 to 400, not really a big deal. Anyway, read to precharge. Honestly, I would try to go for 12. TRDL, actually, I wouldn't expect TRDL to budge. TFAW, I would not expect to change. This may be 18. No, well, maybe. So yeah, with like 1.6 volts of VDD, I would probably try for something like this. But you could also do that at, like, 6200, and, you know, you could run, like, 6200 CL28 or something. So yeah. And also, I don't know if, like, bumping the VDD to 1.6 volts wouldn't cause, like, some massive, like, cause the stability to just disintegrate, which it could. So anyway, But yeah, so that's some, I guess, thoughts on like tuning in 2-to-1 mode. And really the main thing is just like getting your VDDIO and VDDQ voltage just right is very important. Like there's like sweet spots for these, and you kind of need to find them. So AMD's in like 2-to-1 mode is basically as bad as Intel's. Uh, at least it doesn't take 24 hours to find errors. Like so far, like if nothing else, 2-to-1 mode on AMD tends to error out really quickly if it's not set up just right. Anyway, the other thing that the new AGESA sort of brings in, and that's sort of most noticeable, is the DDR5 Nitro mode. Now, I don't actually know what exactly all of these do, and also on the live mixer, running this on auto has worked just fine. Which is why it was on auto when we went into this menu, is like, because I've tried messing with these, like turning this on, but I'm relatively certain that the live mixer actually turns this off, like the robust training mode, I'm pretty sure gets enabled as soon as you go above like, as soon as you're at like DDR5 6800 or something. Because at lower memory clocks, the board doesn't take super long to boot. But once you go past like a certain memory speed, the memory training time drastically increases. So yeah, so you have options basically to increase like the memory training duration, and the idea behind this is like it's going to spend more time making sure that so during memory training, the memory controller is basically trying to figure out how to best talk to the memory sticks. That's like the dumbest way I can put that. The longer your burst lengths that you're doing that testing with, the more data the memory controller has to try optimize the signal quality. So that's why like one of the biggest changes with the 1007B AGSA is like once you're at like 7200 or something, it takes forever to post. Like yeah, it takes a really really long time to post. And I guess if you wanted to, you could try messing around with like shorter burst lengths to like reduce the training time. But the downside to that is, of course, that well, if you spend less time training, your training is going to be worse. And then your like memory context restore might not work, or your stability is just going to be generally terrible. So yeah, and also like I've not had so with the DDR5 Nitro mode, like when I did mess around with this a bit, my priority was to try improve the stability. So I was basically maxing these out for like stability benefits. I think Asrock actually does that on auto because it really didn't make a difference to the training time or the stability. So yeah. Anyway, that's the new 1007B AGSA. It's a big change to it's a really big change to the like memory overclocking possibilities, and from a performance perspective, it basically achieved nothing, which is mostly nothing. Maybe I have other boards that I need to still try this with, but at least on the Asrock boards, like I would still just stick to 1-to-1 mode. Because unless you get 2-to-1 mode to some seriously high speeds, it just doesn't do anything for performance. And it is way harder to stabilize, right? Like the VDDQ and VDDIO sweet spotting like crazy, like that's just not okay, it is a thing in 1-to-1 mode, but it's not as much as it is in 2-to-1 mode. Like it's like 1-to-1 mode is way easier to tune, and I would just performance wise, barely makes a difference. Another thing worth noting is I did all of the testing with a 7950X, right? And the reason I specifically used a 7950X is because it has a lot of cores. So, for something like Y-Cruncher, it can actually use a lot of memory bandwidth. If you run LinPack on something like, say, a 7700X, you're not like LinPack basically doesn't care about memory bandwidth on a 7700X because you have 8 cores. 8 cores simply aren't capable of crunching that much data, right? So you don't need the same level of bandwidth that like a 16-core CPU needs. And even the 16-core CPU doesn't see benefits outside of Y Cruncher, right? So, um, that's kind of the thing is like it's impressive that AMD has gotten gotten this massive improvement out like 2-to-1 mode isn't completely useless anymore. There's like it actually leads to better memory clocks. It just doesn't really lead to any noteworthy performance improvements. So yeah, I don't really see any uh, like it's fun for benchmarking. It's like it's a cool toy basically. Uh, it's not really useful unless you have like again maybe at like DDR5 8000 with the Infinity Fabric synchronized at 2000, um, that might actually be viable and like have performance benefits. But the stability in my experience so far at speeds that high has been so bad that you're probably just better off spending your time in what like putting the time in to tune 1-to-1 mode instead. So yeah, anyway, this video is way longer than it needed to be to tell you that 2-to-1 mode is basically not that useful. But, but here we are. Yeah, so I don't... Oh, wait, I want to do a retrain test. Wait, I can just exit out and discard all the changes. Also, yeah, the if you're on MCR right now, the reboot is really, really quick. Or like a lot quicker than it used to be, even at like 7600 CL34. Yeah, as you can see. So anyway, that's it for the video. I guess I'll leave the specs up for one last time. Thank you for watching. Oh, thank you to G-Skill for the memory kit. And yeah, so thanks for watching. Like, share, subscribe. Leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below as well. And yeah, that's it for the video. So thank you for watching and goodbye.